Okay. So I'm recording this right now, so you guys should see an indicator that shows that it's recording, just so you're aware when I'm recording. The idea is, and I'll send links to this after class, there's a departmental YouTube channel right now that's a private channel. It's not aggregated for the public to find it. And so after class, I'll have these, I don't know the timeline, so there's a box that I drop it in. Some of the IT people in math are uploading them to the appropriate channels. So these will be reviewable on there later. We're using YouTube, just so you know, in case it's interesting for any of you, because YouTube, when you post, automatically closed captions. So for most of the classes, this handles, disabilities issues for some students most easily. Okay, so I just wanted to start just kind of resetting where we are and where we're going and how things are going to work for the rest of the semester. So let me share my screen. Okay, so I want to just go through some of the new tools we're going to be using for the rest of the semester as we're all working from our homes. So my intention is to try to continue to hold lectures at the standard time, if that works for everybody's. Did you guys all just get prompted about if you consent to be on a recording?
Oh, yes, I did.
Okay.
Yeah, earlier. Yes.
That before? Okay. So we'll use this Zoom channel every time. So how did you guys connect? Did you go through the Blackboard link or just you?
Yeah, I used the Blackboard link.
Okay, you did the Blackboard thing. So this should be persistent. So if you just open your Zoom app or whatever you're doing and this meeting ID is saved there, you can just connect through that. You don't have to go through Blackboard every time if you don't want
I did that.
But that certainly works as well. Like I said, I'm going to be recording them and posting them to the YouTube page. If for some reason you felt like you wanted your local copy, you're all welcome to click your own record button and save a local version, although the files are quite huge for these videos. So my intent is to upload this and then delete it from my personal computer so I don't clog it up.
You don't want huge MP4s?
I know. Let's see. Another thing is where we are in the schedule. So we were starting on chapter 6 talking about QED and spin half electrodynamics. So we're about a week behind in the schedule. I think that we should, so this is just copied out of the syllabus, what was intended to be done. I'm going to try to hold to this schedule unless it becomes obvious that we're going to fall behind, but we're going to try to just be more flexible this semester and get in as much as we can with the tools we have available. In order to do that, I expect that I might have to rely a little bit more on you guys doing some offline reading, and hopefully you guys are doing that as you are. So lectures might be a little bit more like I spend half the lecture or 3/4 of the lecture highlighting the key things I want you to know from the chapters, pointing out the key results, maybe not as much full derivation, asking you guys to read through those things on your own and bring questions, and spending more of a portion of class answering questions, since you guys won't be able to find me in my office as frequently. So that means the amount of time I'm going to spend lecturing is going to be shrunk down a little bit. So I'm going to have to kind of trim out some of the derivations and leave it up to you guys studying. So we're going to kind of hit the highlights, but hopefully we'll be able to go over the things that are still important for you to make it through the homeworks. So related to that, office hours, while I'm working at home, I'm not going to keep standard office hours. What I'd like to do is just meet with you guys individually or as a group via some Zoom communications as requested or as needed. Everyone's schedules, I don't know what yours are like, but I've got 2 kids that are no longer in daycare or school, their spouse working. So the amount of time I have in my work schedule is significantly shrunk right now. So I'm having to try to triage and manage that as best as possible. I'm sure it's like that for a lot of you guys as well. There might be home responsibilities you didn't normally have. So I'm going to try to be respectful of people's times and flexible. If, as we're going through homeworks, if for some reason you can't meet a deadline, I'm going to be very flexible on that. Let me just communicate frequently with me and let me know how things are going. Another way that I would like us to try to communicate as a class is through the class Slack channel. So I saw that Jonathan and Kanari were able to find the Slack channel. Brian, I didn't see you on there yet. Is that right?
For some reason, I just haven't even bothered to do that for either class. I guess I'll do that after the class. Okay,
yeah. Why don't you do that after the class? I'm not going to use that for official class postings, but since I'm going to be harder to get a hold of in my office, I would also like the class to kind of work together a little bit more. You know, that's a good way. If you're having questions with the homework, post a little Slack message. I might be able to answer it, but also maybe one of your classmates can help answer it over that, right?
So it's like a group posting for this class?
Yeah, it's like let me show you what it looks like here. Let me pop out of this.
On that note, I have before gotten into Slack, but I do not remember what password I set up, and I've been trying to hunt down that to get back in.
Okay. Do we have Canary connected on Zoom now? I see she's on Slack. No, let me send her a message. So so are you guys seeing my desktop right now?
Yes.
Okay, so this is what the Slack client looks like. It's also web-based, so if you want to just use it in a browser, that works perfectly well. I'm in the Wichita State one. You'll see there's lots of channels here. I set up one called Particles and Fields for this class. It's a private Slack channel, so only you guys that are enrolled in this class are in that, so that you won't get random people popping in and commenting on how you're doing on the homework. And so, you know, it's basically a platform that lets you share files, chat with one another. You can actually, if multiple people are on here, you can start a call with them and do a quick peer-to-peer call through Slack if you want to. And so we can ask Kanari, for instance. So you can do an @ like this, and then the username of the person that you're trying to get a hold of, and that will send them a notification that you're trying to get a hold of them. We'll ask her. And the nice thing about Slack is after you post it, so I just posted that up, so all of you will be able to see it, but I added her, so she'll get a notification that somebody in particular was after her. You know, if you go over here, if you hover, you can get more actions on this thing, and I can go, if I made a mistake, I can edit my message, so things aren't permanent in this. You know, it's not like a text message, so you can go fix that up. You can attach, okay, so she's talking to us. Let me share the Zoom link with her, maybe. Where do I have the Zoom link? I guess I sent it to you guys in an email. Blah, blah, blah. Okay, now you're reading my emails. Okay, great, awesome. Let me see. Oh, here we go.
I mean, it's on Blackboard. I don't know how. She should be able to find it. Okay, got it.
All right, she's trying to connect. Let's pause 1 second so we can collect her before we continue.
Yeah.
Okay. Yeah, I'm gonna use that time to try and figure out my Slack password.
Yeah.
With some coffee real fast. That just took 30 seconds. Hello.
Okay. Canary, can you hear us? No, she doesn't have audio connected. Yeah.
Oh yeah, she's getting something. Dang, man, my camera is connected. I don't understand it.
Hi, Canary. Oh, we can. We can't hear you. Are you? No, you're not muted.
Sorry?
Oh, I heard you very faintly.
Oh, okay.
Yeah, barely.
Yeah, for whatever reason, your audio is very quiet. So let me show you where you might be able to fix that. So if you're on the main Zoom page here, no, I don't think you can see my Zoom controls when I do this, can you? You see my Zoom controls? At the top.
No.
I don't see any Zoom related stuff.
Yeah, okay, it hides the controls. So you might need to go up and play with your audio settings, Canary. The mic gain probably is set down real low. But we're gonna keep going. You can hear us, right? Can you give me a thumbs up if you can hear?
I can hear you.
Okay.
Okay.
So one other thing we can do, especially like for instance, since Canary can't hear us or can't, chime in very loud if there was a question, you all should have a Zoom hand raise option that you can use. So can you guys try to find that? Can you raise your hand if you go to the participants?
Oh, okay.
If you go to Zoom participants, okay, Brian, Jonathan's raising his hand.
Oh yeah. Okay.
Everyone, can you figure out how to raise your hand? If you go to Zoom participants.
Yeah, 1 second. But I can see your screen over here. I cannot see my screen over here.
You cannot see your screen.
No,
So go up to you got to go up to like the very top of Zoom and the little like bar will pop down with some options.
Yeah.
And then you should be able to bring up participants. Mine says manage participants. I don't know what what does it say for non-hosts?
It's participants.
It just says participants 5. It shows me, you, Brian, and Canary, and also a second you.
Yeah, you're there twice.
Yeah, I've got 2 devices connected.
And then at the very bottom, there is raise hand. Yes.
Yeah, you can do all kinds of, all kinds
Go
of.
slower, go faster.
Yeah, go slower.
Are you finding that, Canary?
Yeah,
No?
1 second.
And there's
There are participants over here, so.
Yeah, click that, and then at the bottom of that list, you should see options to raise hands or.
Yeah, I did it.
Okay. All right. Great.
There's a clap.
So that's nice because if I'm talking rather than trying to interrupt me, if you do that, it pops up a little thing on my screen and lets me know somebody's raised their hands, and then I can. It'll just let me. I can finish my statement and then get your question. It'll be a little smoother if you use the raise hand, and you can give me. If I. This is a pretty small group, so I don't know if other of you are using Zoom for some of the classes you were teaching maybe, or if you were a TA, but or if you're doing other things on Zoom, it's useful to use all these little features to get feedback from the group.
Yeah.
Okay, so that's Slack. Let's jump back into the slides. So Canary, we were just working through some slides about how things are going to go for the rest of the semester. Do you see yourselves here? Are you seeing just my screen, or do you see these Zoom windows that are on top of it?
Yeah, I see the little
Yeah,
bars
we
up the
can see
top.
the slides.
Let me move this stuff out of the way. Okay. All right. I'll get better at this as I'm learning how to manage all of these different things for class. Okay, I'll post these slides up. I know, Kinnary, you joined a little bit late, but also this session is being recorded, so you'll be able to look at it later, and I'll send you the link so you can check out the first 10 minutes or so that you missed here. Okay, so I'm gonna put Kinnary's hand down. Okay, so what else is going on? So homework is gonna be a little bit different. We are going to we are going to be submitting homework now via Blackboard. There is a pretty complete web page that somebody in math put together for how to digitize homework and get clean digitizations for you to upload using a phone or whatever things you may have. So if you're having trouble figuring out how to upload your assignment to Blackboard, check out this link. It's pretty useful. I think I sent an announcement on Blackboard for this as well. But right now, homeworks 5 and 6 are already posted and available. And the way it works is when you go to that assignment in Blackboard, there's an option to click and attach a file to upload a file for a homework submission as a PDF or JPEGs or however you want to do it. So just try to get clean pictures of your assignments and upload it there. It's set up so that it allows unlimited submissions up till the due date. So if you post it early and then change your mind, just repost a new one and it's fine until the assignment closes. So don't be shy about posting, or if you want to post the first couple pages, if you do that and post the first couple pages and have a question, I can go find it there if you have questions, and you can keep submitting up to the due date. So homework 5 is supposed to be, I think I pushed back the deadline. That thing is due on Thursday now. So I'd like everybody to give a shot at uploading it on Blackboard, and we'll see how that goes for Thursday. We'll see if everybody can do that, and I'll give you till the end of the day on Thursday to get those uploaded. And then Chapter 6 homework is also available now. Questions about that? Have you guys done online submissions for Blackboard before? This is something new for me, but
Not in a while, but yeah.
okay. I think it's pretty straightforward. So hopefully we can figure it out. We are still going to have a midterm, so I would like to make that available probably this week and give you some time into next week to complete it. I'm still working through what I think is a good amount of time given the current situation. But I'll post something on Blackboard about that probably today or tomorrow and let people know when we're going to when we're going to sign out the midterm. That's kind of it for how we're going to try to operate for the rest of the semester. Are there any particular questions about the technology we're going to use? I think this is we're lucky, at least I am, that this is a pretty small class, so hopefully we can make this happen pretty easily here.
I imagine a class of 20 right now would be a nightmare.
Yeah.
Yeah, you don't get the same experience.
Okay. So this is just a little bit of what we might try to do this week. So we've already spent a decent amount of time just going through. I kind of planned that we probably would spend the first 30 minutes or so today just resetting. So we want to try to get through this week most of Chapter 6. And so we want to talk some about spin some rules, and the big thing we're going to do is summarize all of the results that we've made so far, formally write down the set of Feynman rules that describe so that we can sort of calculate any Feynman diagram that we happen to come across using these set of rules. So that's by the end of this week, or maybe the beginning of next week, Tuesday, we're going to write down all the Feynman rules. Your book in this Chapter 6, they spend a lot of time sort of recollecting all of the derivations and formally showing all the Feynman rules. I'm probably not going to go through every single one because they're available there in your book if you want to see, but I'm just going to kind of capture up the major takeaways for the Feynman rules, and we'll practice using the Feynman rules to calculate some interesting physical properties. And then I do want to continue to talk about experimental techniques and interesting measurements that have been made in the experimental community. And one that's interesting for QED is an experiment that's called G-2. And so we'll highlight that. I'll go through some of those results and highlight how that experiment was done. This sort of is a test of QED at incredible levels of precision. And the results that are coming out of it have some hints that there might be some physics beyond the standard model, and we can touch base on that as we talk about that experiment. What else? Okay, if this is an optional thing, I was gonna see if you guys are interested in this. So I learned that Dr. Salome is going to be giving the Fermilab Neutrino seminar on Thursday at 1 p.m., which falls during this class time. He's going to talk about developing a neutrino detector for spaceflight, this project that Jonathan's been working on as part of his research. And this is a weekly seminar series that they hold at Fermilab. Who's beeping?
Actually, over here, some fire drill will be there. That is why this voice is coming.
Oh no!
This is a fire drill. So is that you, Canary?
Yeah.
Okay, I'm gonna mute you temporarily, and maybe raise your hand for me when the beeping is done, and we'll turn you back on. So if people are interested, we could flip over to this seminar and watch what Dr. Salome is gonna say. Or we could just keep going with the regular scheduled program. So I don't know, what do people think? Are they interested in seeing Dr. Salome talk about? I'm mainly thinking about this because I thought Jonathan might be interested in hearing this because I know he's particularly working on this, so.
It's interesting, and I will probably try and find a recording, but I think since we've missed out on a week of classes, it's worth trying to buckle down on class.
Yeah, I believe they are being recorded. So I can, maybe what we'll do then is I'll just post the link to the recording of this and we'll just keep up with our regularly scheduled program. Okay. All righty. That's all I have for slides. So now we're going to try to lecture. So let me see if I can do that. So I need to share. Oh, interesting. Why is that the case?
At some point, I'll have a question, Dr. Muether.
You have a question, Brian?
Yeah. Okay, so I'm getting like contradictory information from the textbook, basically. In exercise 5.4, it says basically that helicity is not conserved, but we've essentially talked about it, that helicity is conserved, and it says that in exercise 5.14, which is another thing we were assigned. So I'm like slightly contradicted about that.
All right, let me look real quick.
So that sigma is not helicity, that's spin. Helicity is the sigma dot p. You have to dot it with p hat.
Okay. Oh my goodness. All right, that clears up some stuff for me.
Okay. All right, great. Oh, before I start with lecture, we were supposed to hear from Jonathan and Kennery about their
their paper that I should pull back up.
Their references that they pulled up about whatever the assignment was in chapter 4. So maybe Jonathan, do you want to tell us?
Yes, give me just 1 second to find it again and remember what I.
So Kennery, you might. Oh, she's raising her hand. You're still beeping. Kennery, were you trying to ask a question?
Let's see. Oh, she needs to leave. I assume for the fire drill.
Okay.
Okay.
Well, that's life. That happens.
All right, we'll keep recording and you can watch this. We're going to keep going and you can check this out. Please join us back when you can come back in.
Okay.
You can probably stay connected and just leave if you need to.
Okay. So there is my paper. It is the measurement of top quark pair production in a cross-section in dilepton final states containing 1 tau lepton in pp collisions at a particular squared s energy. And it is particularly talking about top-top collision, the decay of top anti-top into any lighter lepton and its neutrino, as well as a tau hadronic decay products of the tau lepton and the other lepton. It was doing this to experiment on lepton universality, and to make the measurements, CERN had a beam of protons for colliding at that particular 13 TeV energy. The highly energetic interactions could produce those top quark-antiquark pairs that very, very quickly decay. I was focusing on tau leptons, and it used they're difficult to distinguish the decays from decays that proceed directly to a lepton. So it focused on the hadronic decays, and it just ignored the leptonic decays entirely, looking for those decays that had the tau hadronic products. And there are a number of other events that could look like those, so they used a bunch of simulation and profile likelihood ratio fits to find out what these looked like. And the final measurement they had was 781 plus or minus various areas, various errors, petabarns, or picobarns is the right direction. It's not a very large cross section. It's a very small one.
Yeah. Okay. All right, great. And so you have the document and you'll send that. Let's see, I guess I don't have an online assignment set up for that. So if you want to just email me your write-up for this, I'll take a look at that.
Okay. I will throw that in its own little mini document.
Oh, she's back.
Okay, good. Probably not an actual fire.
Canary, can you hear us? She's muted. Can you unmute? I can unmute you. Okay, go.
Yes.
Can you talk?
Yes, I can talk about my paper.
Okay,
It
great.
was a paper about the Jefferson lab, and it is calculating the cross sections with 2 methods. One is yield method and another one is acceptance method. So according to me, means I found acceptance method a bit more reliable rather than the yield method. So this is what I found out. And there are means they are using some targets which are titanium, aluminium, carbon, and
Do you have the link to the? Do you have the link to the reference for your publication?
no, I don't have the link actually. Can I email it to the page? Can I email it to everyone after the class is over?
Yeah, or can you find it as we, or yeah, after class is over, you can post it in the Slack message and then email me that, or you can post the link to the document so other people can take a look on the Slack channel. And
okay. I'll try.
And then send me a copy of your write-up on email.
Okay.
Okay. All right. Great. So let me try now to share this. Okay, so I believe people are seeing my iPad now.
Yeah.
Yeah.
Yes.
Okay, let me just clean this up. Why is this so? Okay, so I think we had just sort of introduced chapter 6 when we were interrupted by changes in how the university was going to operate. And so let's kind of remind ourselves where we were. All right, this is going to be a little bit of a learning curve to write on my tablet here. So we're basically in chapter, oops, I need a pen. Okay, so we're in chapter 6. And basically we're going to focus on QED. Sorry, one second. I was going to see if I can add lines to my page here. Nope. All right, I'm not going to play with it too much. I feel like, okay. All right. So, right, basically what we're going to do is repeat what we did from chapter 4, but with our new Dirac spinners that we developed in chapter 5, with Dirac spinners. By the way, is this tolerable? You don't hear annoying, the clicking on my iPad is not too annoying or anything like that?
I don't hear it at all.
Okay.
I haven't noticed it.
Okay, great. So just a reminder that we spent chapter 5 basically developing the Dirac equation so that we could describe free particles that have spin. Right, so we have this description for a free particle, for a free electron, say, that looks something like this. It was some wave function, and it had these UP terms, right? These are these Dirac spinner terms that then have these e to the I, you know, energy propagation kind of terms that go off of it, and they satisfy the Dirac equation, which we wrote down as P slash minus M psi, where now remember psi is this 4-component Dirac spinner, and these P, the P slash, right, that's gamma P, these are represented by these matrix representations that we developed back in chapter 5. Okay, so what do we want to do? So just like in chapter 4, we want to see how the interaction with an electromagnetic field unfolds, right? So basically, what do we want to do now? We have a free particle. We want to turn some interactions on, right? We want to allow these particles to interact with one another. So what do we need to do? Instead of just having P mu, just the free momentum, we're going to write down some operator that looks like P mu plus some additional term that's going to be like the electromagnetic potential that's going to let my particle interact with some potential at space. I mean, we're going to use this sort of limit that we were thinking about before, where this potential that we're going to define in space is sort of local and transient, and we can think about the particle interacting in a set unit of, in a specific unit of time here. We're also going to write down this kind of relationship, that we're going to think about this potential that we have sitting at space being related to this electromagnetic 4-vector, this electric potential 4-vector a mu that we've defined before. Okay. Now, instead of just writing the potential as V, just a potential that we did before, we're going to relate this combination of gamma naught and V to that particular quantity A nu and this, oops, I'm missing a subscript on this matrix here, so that we can operate our 4 vectors on it, okay? And if we do that, the reason we're writing it like that is because now we can rewrite the Dirac equation with our interactions, and it has a nice form that looks something like this. Gamma nu P, gamma mu P mu minus M psi equals psi naught V gamma. Okay. Now remember, again, all of these operators now are matrices, and they're acting on Dirac 4 vectors in this notation. And right, the reason we do this if you do this kind of if you write it in this form, then the potential energy enters the same way for each expression of these Dirac four vectors that it entered in the Schrodinger equation that we saw it in the natural way. Okay, so this is just, remember, essentially giving us 4 linear equations to solve simultaneously for these different components of the Dirac vector, and it's injecting the potentials in the proper places in that linear space. Okay, so we have that, and your book will go through the derivation, but essentially what we want to do then is repeat our first order perturbation treatment from chapter 4. So we want to repeat first order perturbation theory. And when we do that, what we'll find, your book goes through the details. I don't want to work through it because it's very much a repeat of what we did in chapter 4, just with this new notation, is that we'll find that we're able to write down a transition probability. And that transition probability to first order has this form that's going to look like, whoops, what's that? It has this form that's going to look like something that should be very familiar to us. Some sort of electromagnetic current times some, times some sort of a mu over this phase space component, something like this. And what is this J term? J mu Fi, right? We can write it down like this. This thing is just defined now in QED like this. It's the charge times some final particle state that I'm scattering into. There's some matrix operator, the gamma matrices that are acting on my Dirac spinner, right? So I have this sort of vector operation that's acting on my Dirac 4 vectors to give me this sort of current, right? So the way we read it is, this is my initial state. Initial state. This is my final state. Right? And this is my interaction. Operator. Right? Essentially we can write, remember we've talked about that we could write down several forms of the actor. This is the simplest vector form that we can write down to act on this Dirac 4 vector. And so this we can think about, this gives me something like, right, these 3 components together give me some, can I just point on this thing? Let me see. So just as an aside, I'm using Apple's Notepad right now because it writes a lot more smoothly. Zoom has its own whiteboard I could be using, but I found it was really laggy and hard to write on. So I'm going to try to use this, but I might switch technologies the first couple of lectures until I land on one that I like to use. So these 3 things, right, this collection here, right, basically gives me what does this give me? So what is this quantity telling me about? Those 3 things together, what is that?
That's,
isn't that like a current flux?
yeah, something like that.
So it's not, that's not, those 3 together aren't the current flux, right? That's the probability flux.
Well, the E,
and then when I multiply it by the charge, I get this current. Okay, the charge current. Okay, so this basically tells me something about the probability to start in state I, interact with this potential in this vector form, right? We have to go back to get the full transition probability to be over here, right? We're going to take that current, multiply it by this A mu that tells me I'm in an electromagnetic potential, and then that tells me about my transition probability. Okay, and so we can draw, right, the way we represent this as a leg of a Feynman diagram is going to be that I have some incoming particle, ui, and it's going to have some initial momentum, say pi, and then it's going to scatter into some final state particle UF that's going to have some final momentum, something like this. And it's doing that by interacting with the electromagnetic field that has this vertex term that's like EI gamma. This should look really similar.
Yeah, it's exactly the same.
To what we did before, right? Before, what did we have? We had a particle, we had some big J current that was flowing through here that took me from some initial state, psi I, to some final state, psi F. The vertex term was a little different here. It had a form that was like EI PF plus PI mu, something like this, but the character of how we do these calculations is the same. We need something that defines our initial state. We need some term that defines our final state. And then we need something that talks to or tells me how I'm going to allow those two states to interact through this electromagnetic potential. Okay? And the only reason it looks different is because over here on the, right, on the particle without spin, those particles, they weren't for, right, they just had single components. And so that vector component just had to be something that told me about the momentum as it was transferred through that region in that vertex. And right, now instead of having PF plus PI, I have to replace it by these gamma matrices because they have to operate on this 4-state Dirac spinner that is describing the initial state and the final state. So instead of just having a single number essentially that's evolving as I go on, I'm carrying around this 4-component vector. And so things that operate on that have to have some sort of matrix form. Okay. So then we can write down, right? So that's essentially one leg of our Feynman diagram. So then we can look at some scattering processes. So we could look at our good old friend molar scattering. What is molar scattering? This is just looking at E minus scatters to E minus. Okay. We're just going to look at 2 electrons scattering off of one another. We know how to draw the diagram for that, right? It's going to be like 2 leptons. So I'm going to have some initial electron that we'll call particle A. That guy's going to scatter into some final state electron that we'll call B. That we'll call C. And particle B is this other initial incoming electron scattering into what we're going to call the D state. That's this final state electron. And the way they're going to interact with one another is through the electromagnetic potential, and we're going to represent that by the exchange of this virtual photon. Okay? So what we're thinking about is that one particle is cruising along, it generates an electromagnetic field, and the other one is influenced by traveling through the electromagnetic field of that other particle that exists there in space. Okay. And we can see then that this must be related to, right, this current. So there's some current up here that we'll call J1, and there's some current down here that's describing how this particle transitions into its new momentum state that we can call J2. And so the total transition probability, right, the probability of me starting in the initial state A and B and ending up with 2 electrons in states C and D has to involve those 2 currents in some way. And then it also has to know something about the, right, something about the nature of this photon. And remember, we have this quantity that we call Q that we can describe this, telling me about the momentum difference between those 2 particles. And so what does it look like to write out a transition probability for this kind of process? Well, it has to look something like an integral J mu 1 in X, and then I'm going to have another particle J mu 2 over here. And then what goes in the middle here, just like we saw before, we have this Q squared minus q squared term that goes in the middle, right? So every time we see one of these propagators, here's my propagator term, right? That's something that tells me how the momentum is propagating, right? The change in the momentum is being transferred from one side of my system over to the other side of the system, essentially. Okay. So this form, right? This should look almost identical to what we saw in chapter 4, right? I mean, in this compact notation, you wouldn't really know the difference. It's just these J's now mean the full treatment from the Dirac equation. So if I expand this out a little bit, we can see that now inside of this notation is the whole space here. And it's going to look something like minus E, say, going to the C state, gamma mu, minus 1 over q squared. Then I'm going to have a term that's like minus E, what, u bar d is the final state on this side, gamma mu. Okay, and then I'm going to have that integral, right? I'm integrating, right? That top part, I have this integral that's the integral over the allowed phase space, right? I integrate over all the allowed momentum and spatial combinations that I'm allowing my particles to scatter into in the final state. And just like we saw before, that gives me some overall phase term and this delta term, which, let me put it down here. It's going to look like delta to the 4th, PA plus PB minus PC minus PD, right? So this expression just tells us that basically the Dirac spinners transition from a B state to a D state and a U state to an A state to a C state. And we have this propagator term that means they transfer this momentum through the system. And this delta term is going to force us to conserve momentum and energy across this interaction, right? So these final state particles can essentially scatter into any set of final state particles as long as energy and momentum is conserved. And depending on which ones they pick, right, it's going to, right, what that q squared is, as I vary that q squared, it's going to give me different transition probabilities as I go along here. And just like we saw back in chapter 4, this thing here that's, right, this interesting bit that we have to calculate depending on the nature of my initial state particles, right? So this is something for a particular interaction I could go calculate. I could look up the initial momentums and final momentums, and I could write down the wave functions of particle A and particle B, and I could calculate the 4 momentum squared, right? And then to get the transition probability, I would just multiply it by I, and these terms that come from the integral, right? These delta and phase terms here. So this thing, oh dear. This thing is what we were calling M, right? This invariant scattering amplitude. Okay. So essentially, so far, except for calculationally, because I'm dealing with collections of 4 vectors and matrices now, the format for how I'm going to set up one of these calculations looks identical to what we set up in chapter 4, except for I'm using the new formalism here. Okay, so now the big difference is coming in. Oh, so what about this? So this is molar scattering. So we also have this question, what about this process? What if I had A and B and there's a photon and these guys crossed something like this? Okay, so basically here I'm taking C for D, right? Now the interesting thing about this diagram that I just drew is that it is totally indistinguishable experimentally from the diagram above, right? What I would observe in that diagram above is I would have 2 electrons, electron A and electron B, prepared in some initial state. They would come in and scatter, and in my experiment I would observe 2 final state electrons. but I'm not able to, right? The problem is that these electrons, all electrons in nature are totally identical particles. And so I can't tell after this interaction which one of those electrons came from state A and came from state B. So in my experiment, it's totally indistinguishable whether or not I have that top diagram for that lower, from that lower diagram, okay? And we know, we've seen before how to deal with this, right? So we can imagine that this guy perhaps has some scattering amplitude that we'll call M1. This diagram would have a slightly different version that we would call M2, because now, right, this is what I would be calling D. Oops, this is what I would be calling D, and this is what I would be calling C, and there'd be a different relationship for the energy momentum conservation that I would write down. But if I want to find the total invariant scattering amplitude, right, we know that that would just be like the sum, oops, I times this, that would just be like the sum of these two individual pieces. Oops, let me do that a little nicer. Well, that wasn't any nicer. Okay. Okay, so we've seen these before. And what's the relationship here? Well, if you calculate through this, what you'll find is, formally, if you go up to that delta term and play around with your crossing rules that we developed before, right? All this is a crossing diagram where we're just trading C for D. What you'll find is that there has to be this particular relationship that M2 is just equal to minus M1 if I take C and swap it for D. That comes out of the math, but we're going to just use that as a rule going forward, that if I have in my final state any two completely indistinguishable fermions and I trade them in the final diagram, I better get that the invariant scattering amplitude is just minus that of the original diagram. And why is that? It's because they have to still be obeying the Pauli exclusion principle. There has to be an antisymmetric relationship between those two processes when I trade indistinguishable fermions. So we're going to do right. So this is an interesting relationship that we're going to just you can go through, if you want to, go through the calculation and convince yourself that when I trade C for D, I get a minus side popping out. But we can also just take this as a rule that if I trade indistinguishable fermions inside of my processes, that I just end up with a minus sign because of the antisymmetric relationship. There's something else that's indistinguishable about these particles that we have to worry about, right? These things, A, B now, are being described by these U terms. So this may be UA, and this may be UB. And remember what these are, UA and UB. These are those four different fundamental, right, the four different independent Dirac four vectors, spin four vectors, spinners, that I could write down to describe, right, a complete state, right? So we had UA, UB, and we had UA bar and UB bar when we described these things. And that was some complete set of states. I could take linearly, I could take linear combinations of those things to form other sets of states, but we had that basis to describe these spin states here. So any UA or UB is a representation of my particle set up in a particular spin state, right? So UA, if I pick UA1, remember there were four of them, 1, 2, 3, 4. So that UA could be 1, 2, 3, 4. I could prepare particle A in one of my initial states, say. And I could prepare particle B in a particular spin state, right? So there's an assumption here when I write this down is that I know to calculate this diagram, I'm told or I'm able to measure which spin state my initial particles are in, right? And furthermore, this diagram has them scattering into UC and UD. That means that I'm somehow able to identify in some sort of a specific way what the final state, what the spin state is of those final particles. But very frequently in an experiment, you might choose to just send a bunch of electrons in without preparing them in a specific spin state. So if I grab up a collection of electrons in nature and just hold them in my hands, and I try to describe them, right, their spins are going to all be kind of jumbled up, and they're going to be unpolarized, and they're going to all have different spin orientation associated with them. And so it's perfectly valid to do an experiment where I just grab up a bunch of electrons and throw them at a target or throw them at each other without taking care in preparing them in a specific spin state. So how would I then understand what I would expect the scattering amplitude to be in that case? Well, we could throw up our hands and say, that's not very well defined and you need to be really careful about setting up your experiment. Or what we could do is we could just say, okay, I have this collection of electrons and I'm not going to carefully prepare them. So what I should somehow get is the average scattering amplitude if I calculate, right, if I sum over all the different spin states. So what I'm going to say is I'm going to calculate, imagine calculating the scattering amplitude for every combination of initial spin states that I have and every final set of particles that they could scatter into. And then I'm going to take sort of the average scattering amplitude of those and say that if I do an ensemble, right, so if I send a lot of particles in and I scatter them over and over and over again, I should be able to calculate an average scattering amplitude. How? Because I'm going to measure a cross section. I'm going to tie that back to a scattering amplitude. And that that average thing that I measure, I can calculate it just by finding the average value over these different spin sets. Okay, so what about spin? For an unpolarized, oh dear. I don't know how I just did that. Okay. For an unpolarized initial state and unmeasured spin in the final state, okay, what we're going to try to do is calculate some m squared term. Remember, these m squared terms are the things that we can tie to a cross section. We can calculate the square of the invariant scattering amplitude. And when we do that, we can calculate that's somehow proportional to the cross section. And if I do this, right, for an unpolarized state, what I'm really going to be measuring is the average response of these things over all of their spin states. And so I can define this something like this. I'm going to sum all of these invariant scattering amplitudes over all of the allowed spin states. And then I'm going to average over the initial SA plus 1, SB plus 2. Okay. And these S's are the incoming particle spins. Right, so these numbers in the denominator here are just somehow counting the number of initial combinations of spin states that I can have, right? The ways I could prepare the spin for different spin particles, right? If it's spin half, for instance, if SA is a half, one of those terms gives me, a half divided by, or 2 times a half, that gives me 1, plus 1, that gives me 2, right? That tells me I have 2 combinations for that initial spin state. And if both particles are spin half particles, like the electrons above, each of those terms is going to be 2. I would have 2 by 2. That would tell me I would have 4 combinations, 4 ways to prepare that initial state, right? I could have 1 up and 1 down, et cetera, right? I can have those 4 different combinations. And then that second bit where I say sum over all the spin states is you're going to imagine for all those different incoming particles, right, they can also scatter into some final state. So that's going to be summing over all the we'll write down this in a little bit more detail. How are we doing on time, by the way? We have about 10 minutes. On Thursday, we'll get into an example where we show a little bit more detail about how we do that summation over spin states. But essentially, I'm writing it down as a single summation, but you can imagine that we would have to sum over the initial spin states and the final particle spin states, and then average it out over the initial spin contributions. Okay. Okay. Now, that deal, right, calculating this spin averaged quantity, it can get, you know, fairly complicated. So let's see if we can take a look at what this looks at how this looks. So let's see, how would we okay, so how do we compute? How do we compute this term above in our full relativistic framework? Okay. So how are we going to do that? Let's see if we can get started down this path before the end of our time today, and then we'll pick up here on Thursday. So here's what we want to do. We're going to think about, let's use as an example, E minus mu minus scattering. Okay. And we're going to do that for now so that we don't have to worry about the complications of having the indistinguishable leptons, so that we can just calculate one amplitude here. So we imagine that we can identify the muon and the electron separately. So we're thinking about an electron coming in. We're going to prepare it with some initial 4 momentum K. It's going to scatter into some final state electron that's going to have some 4 momentum that we're going to call K prime. The muon is going to be cruising along, and it's going to scatter into some final state muon that we're going to call P prime. And they're going to interact electromagnetically. Okay. So let's try to calculate this. We have all the tools we need to try to calculate the square, right? The spin averaged invariant amplitude squared. So let's see if we can start to write down all the pieces we need to calculate this thing. Well, first of all, we know how to write down just M for a specific state. This thing we wrote down above, E squared, and then we have U in the K prime, U bar in the K prime state. All right, we have to write down this current term. So here's the current. We have the 1 over Q squared propagator term. And then we have a spinner that is in P prime state, gamma mu, UP. Okay, so we know how to write this thing down. So now we want to calculate this spin averaged quantity. We want to square that amplitude, and we want to spin average it. And so we're going to write it down in a form that looks like this. We're going to write it down like e to the 4th q squared, q to the 4th. You can imagine that where that comes from, because when I square that expression above, the e squared and the minus sign and the q squared can just get pulled out in front of these current terms. And then there's going to be 2 bits here that we're going to use this notation. We're going to write L E mu nu L mu nu nu, something like this. Okay. Where what are these things? These things are going to be the spin averaged quantities, right, for the electrons and the muons to scatter into this final state. So let's take one example of this thing. What is LE mu nu going to be? It's just going to be this stuff, right? All we're doing is we're grouping together some of these pieces that we would get for when we square that scattering amplitude in that top line of this expression here. So this thing is going to look something like this. 1/2 sum over the spins And then I'm going to have something that's like mu bar k gamma mu uk. Sorry, that should be k prime uk. And then this guy is going to look like u bar k prime gamma nu uk bracket all of this stuff started. Okay. So this is just taking the terms that relate to the electron piece and basically squaring the amplitudes and summing over all of the allowed spin states and then dividing by the total number of initial spin states, right? So this is 1/2 out in front because the electron has 2 allowed spin states, spin up and spin down. These bits here, right, are just what we would get when I take and I square m here. And when I square that thing, you're going to get something that's like m times m star. And this is just I'm just grouping together the components of that relate to the electron and writing it down in this L term. I would have a very much related term that, right, if I want to write down the muon term, it's essentially the exact same thing. It's just where I have k's, I have p's, and I'm going to sum over the allowed spin states of the muon. Okay. Okay. So now the question is then, what does it mean to calculate this beast, right? The sum over the spin states, what does that mean? How do we actually formally do that for the electrons and the muons, right? So we're going to pause here for today. I'm going to leave us hanging on that. And the first thing we're going to do Thursday is finish calculating this thing. We're going to do one of these summations over the various spin states. It's going to look a little bit messy. We're going to end up, remember, the messy thing about this is all those gammas are these gamma matrices, and all they use are these Dirac spinners. So this is a big summation of a big mess of matrix and vector, right? Matrix and vector operations. And what we're going to see, though, is that this cleans up pretty tidily, and there's some very clean trace relationship or interesting linear algebra relationships that we're going to utilize to simplify this calculation, or at least be able to make some progress. So we're going to pick up there on Thursday. We're going to go pretty quickly through that, and then the rest of Thursday, what I want to do is spend gathering up all of the bits we've seen before and writing them down in terms of Feynman rules. So what we're going to see is that we essentially have developed a set of rules that we can use to draw Feynman diagrams, turn those Feynman diagrams into invariant scattering amplitudes, and then from there calculate any kind of cross-section we want. So we're going to gather up all those bits. We've seen a lot of it so far this semester. We're going to sort of summarize where we're at now, and we're going to see that we have pretty much everything we need to write down the Feynman rules for QED. And then once we do that, we'll draw some interesting Feynman diagrams and practice applying the Feynman rules to those diagrams and see how we would calculate the scattering amplitudes. If we have time, we'll start talking about the G-2 experiment, but that might go into Tuesday depending on how things go. Okay, we got 1 minute. How did you guys think this went? Is this okay, me writing on my iPad? And
yeah, I like it.
Just talking?
Yeah.
Okay.
It's good.
Okay.
So on Thursday, we'll be meeting at 12:30, right?
12:30. Yeah, we're going to try to meet at the normal class times for these Zoom meetings. Does that schedule work for everybody while they're in isolation? Yeah. Okay.
Yeah, it works.
Okay.
I had one quick question before we break.
Yeah.
The U-bar terms.
Yeah.
The bar is a conjugate transpose, right?
The bar is a conjugate.
Because they're taking a vector transpose times a matrix times the vector to get a scalar.
Yeah.
Why don't they use the dagger? Do you know? Is it just a historical thing?
That's a good question. I'll have to look that up. That might just be this author's choice or some notational choice. Yeah, I don't know. Different fields like to use different notation. So.
Oh, I guess the dagger would get in the way of all of the subscripts and superscripts.
Yeah, I think it's just notational clarity, but let me double check that for you and see if there's a reason other than just people like this notation better for readability.
Okay.
So. Good.
All right.
Any other questions?
Not now.
Okay, so do try to get through chapter 5 homework, or people feel like they're on track to have that done by Thursday?
Yeah, there's just one question I thought was really hard, but other
Okay.
than that, everything's good.
So like I said, if you have questions, please try initially to contact me on Slack. Then that lets you get your question out there, and it's sort of the nice thing about Slack is the question will sit there and I can come answer it whenever I have some free time and see it, right? And we don't have to be connected one-to-one. On Slack, if you don't want to put it in the channel, you can direct message me in Slack too. You can just go find my name in the list of Slack people, and you can just start a one-to-one conversation with me as well. But if you post it in the channel, some of your classmates here might be able to help you out before I'm able to get to it. So please try to use Slack. It's a pretty ubiquitous tool at this point. Lots of industries and lots of researchers use this tool. So if you haven't used a tool like that, it's good to get some familiarity with it as well.
Okay, good.
Okay, we're gonna end now. I'm gonna stop the recording.